To understand what it means to say power in an electric circuit, we have to go back to the first semester and recall what power means. As I said then, it's best to think of power as joules per second. You want that to be the first thing that comes to your mind because these joules could refer to the amount of work done per second or a change in energy per second. And that change can take two types. So the word power can describe a lot of different things. Here in circuits, we're concerned with energy change per second or energy change per unit time. And that change can be of two types in general. In the circuits, it's really going to be of one type, a change in energy type. But in general, the change in energy could be a change of one type to another type of energy, say electric to kinetic, like an electric motor. You send electric energy into it, you get kinetic out. Or the energy change could be a change in location. For example, moving water, turning a water wheel. Kinetic energy in the water changes to kinetic energy in the wheel. And again, we could measure how many joules make this change, divide by how many seconds it takes, and that would be a rate of energy change. The unit for that is the joule per second, but it's been renamed. Pause the video, see if you remember the name. It's the watt, named after James Watt. And since it's named after a person, the symbol is a capital W. Why is this important? Well, it's important because the energy is so important. In general, energy is what you pay for. If you use twice as much energy in a month, your electric bill will be twice as high. If you use twice as much energy in a car, you'll have to buy twice as much gasoline and you'll spend twice as much money. So energy is directly connected with money. So if we have, say, a machine that's using up a certain number of joules per second at a very high rate, that will be a very expensive machine to pay for when we plug it into the wall. But if we buy a machine that does the same job with a lower power consumption, a lower number of joules per second, that will be cheaper. We can actually change the power rating of something we plug into the wall from its power rating to joules per second. And since we pay for joules, we actually can change it to dollars per second or pennies per second or money per unit time. Now recall this as well. The idea of energy in circuits and what's going on with the energy in a circuit. Here's a simple circuit with a battery, a light bulb, and a motor. Each circle represents a charge, a coulomb of charge. And when they come out of the battery, they're smiling because they have a lot of electric energy. They go through the light bulb. And as they go through the light bulb, the charges lose some of their energy, but it doesn't disappear. It changes into light energy that comes off the light. So that's the energy transfer, the energy change in the light bulb, electric to light. As the charges go through the motor, they lose even more electric energy, most of their remaining energy. The wheel of the motor turns, so we have electric energy disappearing and kinetic energy appearing. So the one type changes into the other. It would be nice to know, it would be useful to know the number of joules of energy that change type per second. In other words, the rate this is occurring. How many joules per second of chemical energy in the battery are changing into electric energy? How many joules make that change every second? How many joules of kinetic energy are being produced every second? And that's equal to how many joules of electric energy are being used up every second in the motor. So that rate of energy change is a useful quantity to know when you work with circuits. And that's what we just said is power. This is how you would write it in terms of the symbols we've learned for this chapter. Change in electric energy per unit time, divided by how much time it takes for the change to occur. All right, so what the electrical engineer would like is not to have to build some complicated device that will measure power somehow directly, but is there a way to take the quantities that we already can measure easily, voltage, current, and resistance, using our multimeters, or voltmeters, ammeters, and so forth, and use those quantities and calculate the power simply without having to build some new machine that measures electric power. Okay? It's a very simple formula to come up with, because look at what we need. We need delta UE over T, change in electrical energy per unit time. And this is what we already have, these two quantities that we defined at the beginning of the chapter. There's V, and you should pause the video and see if you can get to the end at this point. How can you get an expression for P, or power, in terms of V and I, and possibly R? Well, look at these. Look what you need. You need this, and you need this. You need that on top, you need this on the bottom. So it doesn't take Einstein to figure out if we multiply this fraction times that fraction, Q over Q makes a 1, and we get exactly what we need. But multiplying this fraction times that fraction means multiplying voltage times current. Technically speaking, electric potential difference. That's what that really means, the difference in electric potential between 2 points. But of course, all engineers just call it the voltage across that box. So if we have a box, any electrical device, we can measure the voltage across it and the current through it. If we just multiply these two things together, I times V, it gives us that very important and useful quantity, electric power, telling us how many joules of electrical energy are changing in some sense per second. All right, so see if you can fill in the blanks. What does this tell us? This power, electric power, tells us the number of blank energy either used up, like in a light or a resistor, or made in a battery per blank. Right? Well, it tells us the number of joules of electric energy. Right? Because we're using I and V. It's not just any energy. It won't tell us about a change of kinetic to kinetic, for example, as in the water hitting a water wheel. It won't tell us the change of chemical to kinetic, say, in a person who's running. But it's specifically for circuits, and it specifically tells us about electric energy either being used up or being made in a battery. Per what? Per second of time. All right, at times you'll be working with devices where the resistance is known, and it's very simple to know. For example, on a resistor, you can tell by looking at the resistor, at the color code. When you buy a light bulb, you can often look at the light bulb and tell what its resistance is, although that's a little tricky because devices that get warmer have an increase in resistance as the temperature changes. And generally, for a well-behaved resistor, the resistance goes up linearly with the temperature. So as temperature increases, resistivity of a material increases linearly in a direct proportion, and so the resistance of the object increases. I shouldn't say direct proportion, I should just say linearly. All right, so because R is so commonly known, we'd like useful formulas if R is known. Look at what we have given. We figured this out on the previous board, and this is the so-called Ohm's Law. It's really the definition of resistance from earlier in the class. So look at those and try to come up with a formula for power that has no V in it, and a formula for power that has no I in it. And pause the video, and it's pretty straightforward, right? Look at this, look at this. We want a formula for power, so of course we're going to start here. And no V means we need to eliminate the V. V equals IR, so we'll replace the V with that, and we get I squared R. All right, and then the second one, we'd like no I, so we'd like to replace the I with what it is here. So we solve this for I, plug it in up there, and we get V squared over R. These are used just about as much as the other main formula for power right there, because they're so commonly used with resistors, and the reason for that is the resistance is constant. So this formula here is very convenient because it shows how if you have the constant resistance, say for a resistor, and you change the power, if you change the current, it immediately tells you what the resistance is. So for example, you're running a current through a resistor, the resistor has a constant resistance. What happens if you double the current? What will happen to the power? Well, it'll get 4 times bigger because of this formula. What happens if you double the resistance but keep the current the same? Well, then the power will get 2 times bigger. If the resistance goes up but the current stays the same, the power goes up. Same kind of analysis can be done here. If you double the voltage, hold the resistance constant, the power will get how many times bigger? 4 times bigger. If you have a constant voltage source, say a battery, and you keep increasing the resistance, what will happen to the power consumption for what you're taking out of the battery? If the resistance gets bigger, since it's in the bottom, the power will go down. So these formulas are very useful, and test makers and textbooks like to ask you those kind of questions. Use these formulas in that common way of if I change one variable, what happens to the dependent variable? All right, we didn't mention this earlier. We looked at a light bulb and a motor and a battery, but you should know what happens in a resistor. So, by the way, in a resistor, the initial electric energy is changing into what type? What possible type can it change into? Resistor doesn't give off light. It doesn't move, so there's no kinetic energy. There's no chemical change. There's no chemical energy. It doesn't make sound. All these things, what's left? Well, you have charges going through a resistor and making collisions, and they're making the parts of the resistor actually vibrate in place. So what's happening to that resistor? It's getting warmer. So the kind of energy that is created in a resistor is always thermal energy. And in fact, an electric heater, like the coil on top of a stove, like that, the coil on top of a stove, It's not a very good coil drawing. That's really basically a resistor. It's getting warmer. So it changes into thermal energy. And for this reason, resistors are in a little case, and if you need them to be able to process more higher power rating of thermal energy, to more joules per second going through the case and out into the atmosphere to keep the resistor from overheating, you put it in a bigger case. So bigger resistors, physically bigger, don't actually have more resistance. What they're able to do is handle more power, handle more thermal energy being produced in them per second without melting. So all resistors come with a power rating, and that tells you the maximum power you can put on them before they melt. Typical power ratings might be 1/4 of a watt to 2 watts, or even 5 watts. And that's a pretty big, in everyday life, a 5-watt resistor is a pretty big power rating for a resistor to be able to handle that kind of dissipation of thermal energy. And then finally, since we recently got an electric car, I'll run you through the numbers of how our electric car, the kind of things I look at when we're charging our electric car. And charging is a bad word. You're not putting charge into the battery in the car. What you're putting in is energy. You're running electrical energy through it, and it's changing into chemical energy. But charging is the common expression. Right? Here's the voltage on, that's not the typical voltage in a typical wall socket. That's the double voltage where you have the strange socket that might have 4, I'm not sure I'm going to draw it right, but I have 4 or 3 outlets like that. That's the 240 volt outlet in your house that you might plug an electric dryer into. Your air conditioner is plugged into that double voltage. The current the car draws, typically the maximum it's allowed to draw is 30 amps. So from this you can figure out the power produced. All right? And of course you get 7,200 watts. But engineers aren't going to say 7,200, they're going to say 7.2 kilowatts. That's what's written all over the spec sheets for the car and for the charger. So figure out how much energy would be added. If that's the power, that's how many joules per second, figure out how much energy will be added in an hour. And if I remember correctly, this is 26 million, yes, 26 million joules. That's really big to deal with, and you could change it to 26 megajoules, but a common unit that's become established when charging cars or dealing with household and domestic and industrial power and electric energy is the kilowatt hour. And a kilowatt hour means instead of multiplying by 3,600 seconds, you just multiply this by an hour. So 7.2 kilowatts, that means in 1 hour, you would transfer 7.2 kilowatt hours of energy into the car. So this is a unit for energy, the kilowatt hour. To convert it to joules, you replace that hour with 3,600 seconds and you get the 26 million there. And of course the K means 1,000. It takes a little while to get used to this, but kilowatt hour is a unit for energy. It's yet another unit for energy in addition to the thermal calorie, the BTU, the nutritional calorie, the erg, the joule, and now the kilowatt hour. So the kind of rule of thumb I just did today looking at our electric car specs, 7.2 kilowatt hours is how much energy the car receives in 1 hour. It holds 75 kilowatt hours. That's what the battery capacity is, 75 kilowatt hours of energy. So it takes roughly 10 hours to completely charge our car. And driving around on surface streets, we get about 4 miles per kilowatt hour. That means the range of our car, since we can put in 75 kilowatt hours of energy and we get 4 miles for each, that's about a 300-mile range. It's usually a little bit more than that. And it also means, look at this, if that's the power, 7.2 kilowatts, and we get 4 miles per kilowatt hour, that means every hour we are putting about 29 miles onto our car when we charge it.